So in this question, we have a solution that consists of molecules of HA as well as molecules of A minus. HA would represent a weak acid and A minus would represent its conjugate base. We have some known information listed here. We have the volume of the solution, the molarity, as well as the pH and the pKa of that weak acid. The first thing that we want to do is take those data and use them to determine the total number of moles of these solute particles. So in other words, we want to figure out the total number of moles of HA and A minus added together. That's a relatively easy task because we know that the molarity of this solution is going to equal the moles of these solute particles divided by the volume. Multiply both sides of that equation by volume, so you'd have volume times molarity is equal to the moles. Now the volume is given as 100 mils, just divide that by 1,000 to get it into liters. You have 0.1 liters, and then multiply that by the molarity of 1 molar. And we can see that the number of moles of solute particles is simply 0.1. Now that is the moles of both HA and A minus added together. So we could represent that as follows. We could say the moles, we'll use N for moles, the moles of HA plus the moles of A minus is going to equal 0.1. That's great, but we can actually figure out the individual number of moles of HA and A minus. And we can do that by taking these data and inserting them into the Henderson-Hasselbalch equation. Let's take a look at that formula. So there is Henderson-Hasselbalch, and we can plug in the given pH of 8 as well as the given pKa. The next thing that we would do is subtract 7.4 from both sides. And so now we have 0.6 is equal to the log of this ratio of A minus to HA. Now, we wish to cancel the log on both sides. Let's not forget from perhaps a pre-calculus class that we have a base 10 here. And if you want to get rid of a log, you'd actually have to raise 10 to both sides of this equation. 10 raised to the log base 10, those are inverse operations. They cancel each other out. That leaves you with the ratio of A minus to HA on the right side. On the left side, pick up a calculator and just raise 10 to the 0.6. You're going to get about 3.98. So what does this mean? Well, we can actually put that 3.98 over a 1. That would tell us that the A minus could be represented, this would be the moles of A minus, so we'll use that N. The moles of A minus could be represented as 3.98x, and then the moles of HA, you can see from the ratio, would be represented as 1x. Now, of course, the total number of moles, N A minus plus N of HA, would be 3.98x plus 1x, which is 4.98x. Now we can actually figure out the value of x because recall earlier that we said that the moles of HA plus the moles of A minus was 0.1. So we can actually come down here and fill in 0.1 moles into this formula. And then we will divide both sides by x. So 0.1 divided by the 4.98 is going to give us 0.02 roughly. So that's 0.02 moles. That's going to equal our x. Okay, well, that's great. Well, just look back here again. We had those expressions for the moles, so we can actually slide over here. Now we can see that the moles of A minus is going to equal 3.98 times our x, and then the moles of HA is going to equal 1 times our x. Let's pick up our calculator and simplify the top one. And you're going to get approximately 0.08 moles, and the bottom one, of course, is still 0.02 moles. So now we know the moles of HA and the moles of A minus. That's all the initial conditions of this solution. Let's put those numbers on hold for a moment and just go back and reevaluate what's happening. Somebody is adding 30 mils of 1 molar HCl, 30 mils of 1 molar HCl. So, of course, what's going to happen is that the HCl, being a strong acid, is going to react with the conjugate base. It's going to react with the A minus that's floating around in the solution. And because HCl is a proton donor, it's going to donate a hydrogen over to that A minus, and that's going to form the product HA. and it also forms Cl minus, which is a spectator ion, doesn't have any influence on the pH, so we can actually disregard it. Now what we can do is create an ice table. And we have calculated the initial number of moles of A minus. You may recall that that was 0.08 approximately. And then for HA, it was 0.02. Again, we had calculated that earlier. Now we just added 30 mils of 1 molar HCl. Recall that the moles of HCl would equal the volume, which is 0.03 liters, notice the conversion into liters, times the molarity of 1 molar. So we work that out and we get 0.03 moles. That's the initial number of moles of HCl added to this solution. Now the reaction goes to completion because HCl is a strong acid. Going to completion means that the fewest number of moles will be reacted. It's a limiting reactant problem. So if you look at the initial number of moles of HCl and the initial number of moles of A minus, you just ask yourself, well, which one is the fewest number of moles? And of course, that's the 0.03. So we're going to subtract the 0.03, allowing the HCl to completely react. It goes to 0. This will also reduce by the same amount, so we subtract those two and we get 0.05. The product will be formed. Remember, as reactant is diminished, as the number of moles decreases of the reactant, the number of moles of the product goes up. We are making product. So that's going to go up by 0.03. And we add the 0.02 to that, and we get 0.05 at equilibrium. So actually, the moles of A minus and the moles of HA are going to be equal at equilibrium. So now we can actually calculate the new pH using Henderson-Hasselbalch. Remember, that's equal to the pKa plus the log of the ratio of the conjugate base to the weak acid. We can just plug the numbers in. The pKa was given earlier in the problem. It was 7.4. So we'll fill that in. And again, the moles of A minus and HA are both known. Now you'll notice you get 0.05 over 0.05, which is 1. The log of 1 is 0. You can prove that on a calculator. This means that the pH after adding the HCl is equal to 7.4. That is the correct answer to the question.